Thank you, Ahia. Thank you, everyone, for joining this session. This session is going to cover the basics of how we can use large language models to build apps that are useful for the general public. So this session is going to be from the perspective of a beginner. So we would start with the basic intuitions, and then we would show you simple examples on how to work with LLMs using APIs and so on. Okay. So if you have any questions, I request you to keep it for the end. But if you want me to repeat or give some more explanation on some of the topics, please interrupt me. But for questions, please keep it to the end. So this will be our agenda. So we would start with an intuitive introduction about LLMs. And then we would see how to interact with LLM via APIs. And then we would see what is RAG, why we need it, what are the components of RAG, and then we will show a small demo of a simple use case. Okay. Now, so let's imagine that we have this task that we are going to predict the next word in a sequence. Now, this is the sequence that's given. The cat likes to sleep in the, and then there is fill in the blanks. So what word comes next? Okay, this is the problem that we are trying to tackle. Okay. Now, let's say that we have 50,000 possible words from which we can choose one word. So you can see it as that being 50,000 different classes. Now, this problem is something that is easy. We can frame it as a machine learning problem, and it can be treated as a classification task. So basically, we are going to come up with a model that decides which class to select for this given statement. So you pass the statement as an input to the neural network, which we train with many examples. And then what it does is it picks the word that has the maximum probability. So which is box in this case. Okay. Now let's look at the training setup. Okay. With just one sentence that I showed earlier, we can actually create vast amounts of sequences. So the purple ones is basically the input that's given to the model. The orange is the fill in the blanks or find the next word. So the model doesn't know this orange word yet. We just pass this first word. In the second example, we pass the first two words and we ask the model to find out the next word. So like this, with just one sentence, we can create multiple sequences. And the same method can be extended to even longer sequences. So here you can see a very long sentence, which is in purple, that's the input. And then the orange one, which is the word that needs to be predicted. And the same thing can also be extended to code. So in this case, we have input up until here. And then the orange is the prediction that the model needs to make. This is not given to the model yet. So when we train it with such a large corpus, what happens is the model becomes really good at predicting what is supposed to be the next word. Now, let's see how we can use this and come up with a sentence completion, right? So after training, what we do is we pass the input and we ask let's say the LLM to generate what's the next word. So the input is a trained language model can. The model says generate is the best word. So we use that. And then we use this as input again, along with the previous input, and then ask the LLM to generate the next word. So you get coherent. So then you use coherent and then the previous text that's available and ask the LLM to generate the next word and so on. So you repeat this until you reach the end of the sentence or a logical end. Okay, that's how the prompt completion happens in large language models. Now, the large language models, right? So the large is basically, it tells us that it uses large amount of data for training. It has a large number of parameters in the model, and it requires a very large infrastructure in order to train the models. as a result of all these large things, what has happened is the model has encoded the nuances of language within its parameters. And especially this has to be said, it's predominantly English and a few other European languages and maybe Chinese. Okay, but then it has not understood anything. Okay, it has identified just the patterns and relationships that exist in the language, and purely based on the way data was given to it during the training process. And it has also memorized most of the internet's information within its parameters. But still, what we need to keep in mind is that it's still a probabilistic machine. It is only going to generate a probability distribution of the next word based on the given sequence of words. So it's a conditional it's being generated, which is conditioned on sequence of words. And then it comes up with the probability distribution, right, for all the possible words in its vocabulary. Then it picks the best word as the next one. And so on. We can repeat it until we get the end of the sentence or when we reach the limit. Now, let's intuitively understand how these models are trained. So let's understand the steps that are involved in coming up with an useful for people to interact, let's say like ChatGPT. Let us imagine that there is a restaurant owner, and the restaurant owner is having prompt chefs. The restaurant, the large language models process and things that, let's say he can, so he picks a bot, and then what he does is he picks recipes that he can get hold of. So he gets all these, and what he does is he then picks out every page from that recipe book. And what he does is, like we saw before, we withheld some text and we asked the model to predict the next word. Okay. Is everybody having problem?
No, yeah, there is no problem. No, in the beginning there was an issue. So yeah, you
Okay.
can go ahead.
All right. So we redact few contents from the text and we train this bot. Okay. So we do the training loop, and it's a massive training set that we use. And then we come up with this bot. Now, let's see what this bot can do. So if we say a blueberry cheesecake, what it says is recipe requires 100 grams of blueberries. So what it is doing is it's continuing the sentence. It's good at that. But let's say we give this question. We say, what can I make with avocado? But then the sentence has ended. So there is no logical next word that it can predict for that sentence. So what it does is, because of the training that is done, it sees that, okay, based on this question, I can pick similar questions. What can I make with bell peppers? Now, this is a problem that we need to rectify. But this process that we just saw, right? This process is what is called as generative pre-training. And what happens is the model becomes, or the bot becomes exceptional in predicting the next word. Now, let's say the restaurant owner picks the best chef and asks the chef, okay, how do you hire a chef? What questions do you ask from the chef, ask to that new hire? And what response do you expect from that person? So this chef, let's say, prepares the question or the instruction and response, the expected response, or the good response that is expected from the
Punya,
person.
again, it's voice is cracking first.
Okay.
Is that for
I
everyone?
think it's probably to do with my internet. Okay. Is it better now or is it getting worse?
It's better now, Punaya.
Okay, all right. So this chef prepares this data set, which is basically the instructions or the questions and the expected responses. And then we train this bot that was already trained in the previous step. And we come up with this bot. Okay. Now it is a mix of two because there is a good bot in there and there's a bad bot in there. We'll see what it is. So now if you ask this bot, what can I make with avocado? It says you can make guacamole smoothie, and it goes on and on. But let's say we ask something like this. let us make a spicy curry. Now this bot says, okay, let's add 200 teaspoons of red chili powder, but nobody would add 200 teaspoons, right? So the bot is good at following instructions, right? But it doesn't know if the responses are actually correct or not. And this step is actually called instruction fine-tuning or supervised fine-tuning, or just shortly instruct tuning. Now let's say what we do next is we ask the bot to cook the recipes and serve it to a human being, and then find out the response of the human being. If it's a good response, that is, if the human likes it, then we give a reward to the bot. If it is, we give a penalty, and this is called a feedback. And what we do this, we continue this process, okay, again and again for multiple examples. And at the end of that, this bot becomes aligned with the expectations of the human being. Now, this is a good bot. Let's see. If we ask this question, or if we give this input, it says, okay, let's add 2 teaspoons of red chili powder, which is aligned with what a human would be okay with. Now, this is called reinforcement learning with human feedback, because the responses are aligned with human values. Now we can take this bot and we can deploy this. Now, most of the interactions that you have, let's say with ChatGPT, that is at this particular stage. Okay, so there is a generative pre-training or pre-training, then a supervised fine-tuning, and then an RLHF, which is reinforcement learning with human feedback. So at this stage, the bot is ready for end user consumption. But let's say the restaurant owner thinks, okay, this bot can cook any recipe, but I want to give this bot some persona. I want this bot to cook like my grandmother. So what the restaurant owner does is he picks out his grandma's best recipes, and then he knows what the chef did. So he prepares another data set, which is basically derived from this grandma's recipes, and then he trains this bot. And what happens is you end up with a chef that cooks exactly like his grandma. So he says, make me some yummy lunch. Then the grandma says, the bot says, okay, dear, I will make my signature, and on and on. Now, this is called fine tuning or domain specific or task specific fine tuning, because it can adapt to a specific task or persona or a domain. Now, this is an optional step. Okay. Let's say there is a different use case. Now, let's say that the owner has a secret recipe or set of secret recipes that he doesn't want to share with every chef in the restaurant. So what he thinks is, okay, let me leverage this bot to use those recipes. So now he takes his vault, he goes there, and then whenever a customer places an order, right, at the restaurant, he goes to the vault, picks the secret recipe, and then creates the instruction along with the secret recipe and passes it to the bot. And now the bot can actually cook secret recipes that only the restaurant owner knows. Now this, let's say you ask this question, what is the secret sauce made of? The bot at this stage, right, would not know it because it doesn't have access to the vault. Whereas this bot knows it, and it can say, I use a special mix of whatever herbs and spices the owner uses, right? So this is basically retrieval-augmented generation, because it has access to facts that it previously did not have access to. And it's usually used to ground the LLM, right, to facts. Now, let's come back to the LLM world again, where what we discussed is exactly summarized here in terms of LLMs rather than the current scenario. So you can see here for generative pre-training, what happens is we need to use unstructured data, and it's in the order of gigabytes, terabytes, and it's approaching petabytes. And it's collected from Common Crawl books and everywhere from the internet. Now, this is a self-supervised training that happens because you saw that we basically redact some of the contents in the text and we train the LLM. Now, some examples are given here, GPT-3, PaLM, T5. These are examples of just pre-trained models. These are also known as base LLMs. Now for instruction fine-tuning, we use specifically curated data sets of instruction and expected response, that is prompt or query and expected response. And this data set is expected to be in the order of 50,000 to 100,000 pairs of expert curated prompt and expected completions. Now, this includes multiple tasks like question answering, logical reasoning, mathematical reasoning, and so on. So that's why the order is 100,000 samples. And this is a completely supervised training. And some of the models are Instruct GPT. So basically GPT-3, let's say it's trained to follow these instructions, then it becomes Instruct GPT. Then Palm trained on Instruct dataset becomes Flan Palm, Flan T5. So Bloom becomes Bloomzy, and Llama becomes Alpaca. Actually, Llama 2 becomes Alpaca, I think. Okay. Then comes reinforcement learning. So here, you know that a human is going to validate the responses, right? So the data set is called RLHF dataset. And here we have the prompt and then the LLM generated completion, because earlier you saw that the bot cooked it and served the food. So here we need the LLM generated completion. And then the human is going to rate the LLM generated completions. And based on this data set, we are going to use reinforcement learning techniques to fine tune this particular LLM. So we come up with a human aligned LLM. So ChatGPT is one such model, GPT-4 or Llama Chat. Now, what happens is in some of the scenarios, both these stages are combined and you get a model which is base LLM, and straight away it goes to a human aligned LLM. They don't release anything in between. That's also possible. Now, let's say we want to fine tune the LLM, the human aligned LLM, for a domain specific task, right? Then what we do is we need to again prepare instruct dataset. This is exactly same as what we saw in this step, instruction fine tuning. But the difference is it's going to contain information pertaining to the tasks of interest or the domain that we are interested in. For a single task, we can use just thousands of samples and we can fine tune it. But for multitask, we still need the same order, which is 100,000 samples. This is also going to be supervised training, but then this is different from the previous supervised training here because we are not going to change. We usually do not want to change the models of the human aligned LLM. Rather, we want to add new parameters and then train or adjust those parameters. So that's where PEFT comes into picture. But some companies, they might also go ahead and do a full fine tuning where even the parameters of human aligned LLM will get changed during the training process. Now, some examples are FinGPT, ChatLaw, MedPalm, and so on. And then the final step, the final section here is the RAG, or the Retrieval-Augmented Generation. So here you can notice clearly that there is no training involved here. In all these previous steps, there was some form of training, but here there is no training. All you're going to do is you're going to basically do a document collection, right? And you're going to store it in a database. So those can be companies' internal data or some task-specific update data. Now what happens is the query comes in, goes to the database, retrieves the context, creates the prompt, sends to the LLM, and then gets the response. So you have chat PDF and few other, many options are out there in the market. Now you know how LLMs are trained. Let's go and see how to interact with LLMs. So this is something that everybody will be familiar with. This is ChatGPT using the ChatGPT 3.5 model. So I don't have to explain anything further here. You know how to give an input and get an output. But this is something that many of you might not have used. This is on Hugging Face portal. So there are some models which are available as inference endpoints, and they have this nice UI where you can give in some prompt that is text, and you can click the compute button and you can see the completion. So this is the case for Google Flan T5 base. You can see here, this is just 248 million parameters. It's a very small model. So basically the output is garbage. But here you can see this is Mistral's 7 billion parameter model, right? This is 7.24 billion params. Now, I gave the input as large language models R. All these blue things are auto-generated. This has a different user interface compared to this. So you can see here, this is pretty good for a 7 billion parameter model. For ChatGPT, we actually do not know how many parameters it contains. There are only guesses. It's in the order of hundreds. In the sense, 100 billion parameters and more. Okay. Now, so LLMs can be accessed. We just saw the user interfaces, right? So, and we saw two different types. One is a proprietary LLM, like a ChatGPT, and then the open source LLMs, which we saw from Hugging Face. Now, we saw the chat UI and we saw the Hugging Face endpoints. But then there is another way of accessing LLMs, which is via APIs, API endpoints that are provided by the proprietary LLM providers. So all we need to do is give an input text and invoke the API, and we get the generation out. Whereas in the case of open source LLMs, we need to do a custom deployment. So the model weights are available. So we need to have the infrastructure. We need to deploy the the LLM, and then we need to make the inference. Now this table here summarizes everything about these 4 different methods. So what we'll focus on is the API endpoints and custom deployment, because UI and this UI, we don't really bother because that's not of interest for our project. We want to focus on these 2. So the key thing to notice is the API endpoints and custom deployment of open source LLMs, they are applicable for the business use cases and for any apps that you want to build. The problem is, for proprietary LLMs, the model weights are not exposed, whereas for open source, we can get the model weights. The good thing about the proprietary LLMs and their endpoints is that they are hosted by the LLM provider themselves. So they manage the infrastructure and their performance is enterprise grade. And they provide best-in-class responses because their models are bigger. The problem is, it is not free. There is a limited free trial, but there are limitations on how many times you can invoke in 1 minute. So those limitations are there. Whereas in case of open source LLMs, we don't have any such limitations. There is no pricing problem as long as we have the necessary GPU. Okay. But then the challenge is that we need to deploy that at our own infrastructure. And the performance is heavily dependent on the GPU capacity and the size of the model that we choose. Okay, so these are the trade-offs. These are the 2 things that we need to look at and come up with a trade-off. So you can see here, ChatGPT 3.5 uses GPT 3.5 model, and Bard uses Google Palm model. So when you say ChatGPT 3.5, that's the UI, and Bard is a UI. Whereas here, the endpoint from OpenAI for GPT 3.5 is GPT 3.5 Turbo. Similarly, for Google Palm, it's text bison 001. For open source LLMs, these are from the Hugging Face model repository. So you can see those here. Now, before we understand how to work with LLMs, we need to understand the process of tokenization.
One small doubt.
Yeah.
So all the Hugging Face models are open source or free, right? All the Hugging source.
That's my understanding. If they're exposed, they're usually open source. Otherwise, I mean, we need to check the license because some of them may not be explicitly open source, but we need to check the license to be safe.
Okay. But usually it is free source.
Yeah.
Okay.
All right. So we have a lot more to cover. So if you can keep the questions to the end, that will be good. Okay. So now on the left, you can see that there is an image and it has RGB 3 channels, red, green, and blue. And the process of capturing image naturally captures them in the form of numbers. So there is a natural and direct representation for images. And this can be fed into the machine learning models as it is. Whereas in case of text, we need to break it into smaller parts, okay? And then encode those smaller parts to numbers. Only then machine learning models or machines can actually process them. So let's take this sentence here. Let's do tokenization. This is a text. Now what happens is in the first step, let's say we use the process called subword tokenization, right? Where in this method, we keep the frequently used words as is, but we would split the rare words into multiple parts. So you can see here. Now these are special tokens added at the beginning and the end for the models to understand when it starts, when it ends, and so on. Now you can see let, do, and let and do have come as it is. I mean, even let's has got broken into let, and then this apostrophe, I mean, the quote, and yes. Whereas tokenization is split into token and this word. So this will be some meaningful subword. And then we take each of these words and then we encode them. Okay, this is as good as having a list or having a dictionary, right? Running from 1 to n being the number of words in the vocabulary, and assigning and picking a number for each word from there. Okay, that's all there is. Now this number is passed to the machine learning model. Now the vocabulary is available with the tokenizer. So when we have this number, we can decode it back to the original text. Here you can see the code for that. So we are using something called as auto tokenizer from transformers, and we are using the BERT tokenizer. Tokenizers come in different forms. We are using one of them, which is BERT. This is the same text. All we are doing is we are calling the tokenizer function. We are passing the text, right? And then it returns something. And here I'm only using the input IDs from there. Now, as you can see, so we can also decode each of the token IDs and we can retrieve the word. So this is the decoded text here. The input is this. There are 9 tokens generated, and these are the tokens, and these are the corresponding token IDs. And then this is the decoding of the token IDs back to text. You can play around with this code on Colab, and you can try different text and see how it works. Now, tokens are important. That's why we are talking about them, because they are the common thread between context length, chat history, and the pricing. So every LLM has a finite length that it can process. So that's basically the number of tokens a model can process at once. And if you want to relate it, let's say you want to summarize something, right? Then you can only summarize a text that is as long as the maximum tokens allowed. Okay. Now, in case of OpenAI, there is a challenge there because they consider context length as the sum of input tokens and the output tokens generated by LLM. In case of GPT 3.5, it is 4096 tokens, and Llama 2 is also same. Now, chat history. So models or LLMs themselves do not have any history. They are stateless. So once you give an input, what happens is it generates the output and it's done because it goes away from the memory. So if you want to have chat history, then developers need to track the chat history, and you need to include the history along with every single input. That's the way the LLMs work. So the downside is that longer the history, what happens is the next input becomes shorter because you have a context length limit that you're working with. So that's something that you need to keep in mind. And there are options available to manage that. That is, we summarize, let's say, the history and pass it as a short text rather than the entire text as it is. Now, pricing, this is applicable for proprietary models because they charge us based on the number of tokens we consume. And it's tokens, it's not words. Now, there is a rule of thumb, right? So you have seen earlier that words can get split into multiple subwords. So the subwords are actually becoming the tokens. So the rule of thumb is 1 token is usually 4 characters or 3/4 of a word. So 75 words equals 100 tokens. Now, for OpenAI especially, this is the rate limit. For input, there's a rate, and for output, there's a different rate. Okay. Now you know how to tokenize. So let's see how to interact with LLMs. On the left, you see the code, which is for OpenAI, or on the right, you see the code, which is for open source LLMs. So you can see here, I'm just importing OpenAI. I'm using this library just to load the .env file where I'm storing my secret OpenAI key. So load.env basically loads this OpenAI key into the environment. I'm using an instruct model of GPT 3.5, and I'm giving a prompt which says, write a vision statement for an AI for good company in 20 words. And I'm just calling the client, right, OpenAI .completions.create, I'm giving the model, I'm giving the prompt, I'm setting temperature to 0, and I'm telling the maximum output that I expect is 200. And you can see here, it has generated a nice vision statement for this company. Now let's see how an open source model performs, right? Now, as you can see here, the code is much longer because you need to do a lot more work for working with open source LLMs. You need to use the transformers library, right? Use tokenizer and use this auto model for causal LLM. And you need a GPU. Without GPU, you cannot do much. And I'm using a Mistral 7 billion instruct model here. And you can see here, the prompt is very different or slightly different from what I gave to OpenAI. So these are the special tokens or special keywords that you need to pass for this model, not for every model, but for this model I have chosen. Okay, then I'm tokenizing the prompt. That's what I'm doing. So I'm initializing the tokenizer, tokenizing the prompt, sending it to GPU, and then I'm loading the model, right? I'm loading the model. And what I'm doing different here is I'm loading it in 4-bit quantization. Now you can see here, I've installed bits and bytes here because this model cannot fit the GPU memory of Colab. So I need to load it as a 4-bit quantized version. So that I'm doing here. And then I'm just calling this LLM.generate. I'm giving the tokenized prompt. Here it was just the text, but here it is the tokenized prompt. I'm saying 200 tokens again. And then once I get the response, right, here I'm doing decoding, right? I need to decode the output because what I will get as output is not text. I will get token IDs as output from the LLM. I'm decoding it and I'm showing it here. So you will see that the model includes the input, right? Whereas here it was just the output. So that's something that you will notice with open source models. So you can see the actual output here, right? Empowering humanity, one intelligent solution at a time for a better, more equitable world. Looks like open source LLM is much better than ChatGPT 3.5. I'm sorry, GPT 3.5 Turbo Instruct. So I will share the notebook so you can run them on Google Colab and you can check with different prompts and different models. Okay, now there is something called as chat completion models. Okay, chat models and completion models. What we saw earlier are completion models. So chat models are slightly different. So the difference is this. So the completion model, we say the square root of 49 is, and then this blue crossed one is basically the output. If we want to use a chat model, we need to give input, that is the prompt, in a different way. So we have to give a set of roles. That is, it will be a dictionary. The role user will be the question. So here we say, what is the square root of 49? And then we need to also pass assistant and leave it empty, right? So the output will be square root of 49 is 7. So the difference is, instead of giving just text, we need to pass a dictionary. And within that dictionary, the keys of the dictionary mention what role the content belongs to. Now let's see a code example here. Okay. Now this is the example for OpenAI. So you can see here, this is a chat model. So we are going to use multiple responses, okay, so that you can also see how the history is passed. I'm using a different model here. This is GPT 3.5 Turbo, not the instruct model, because in OpenAI, the instruct model does not support chat, whereas this model supports chat. So here I'm using role user. So basically the end user said, what is your favorite condiment? The assistant replied in a previous iteration. Okay, it said, well, I'm quite partial to blah, 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 right? It gave that. And then the user now has said, do you have mayonnaise recipes, right? You can clearly see there is a role used here. Role is user here, role is assistant. Now we pass the messages as input. Now you can see here, there is a slightly different signature. I'm using a different function. I'm using a chat function. I'm passing this model, I'm passing messages, and then we get the response out. When I show the notebook, when we have time, I'll show the notebook. You can see the response there. Now, in open source LLMs, this is going to be different. Okay, yeah, we are going to set it in the same way. This messages is exactly the same here. But then what we are going to do is the tokenizer, we are going to use a different thing. We are going to use an apply chat template tokenizer because we have a set of messages with different roles. So this apply chat template respects the roles and then creates the tokens respectively, accordingly. Then I'm using the same approach here, right? There is the same step where I load the model and then I do the generation. But here, the decode is slightly different. I'm using a batch decode because I'm getting a bunch of messages. All right. So these are the differences when we use a chat model in open source LLMs. Now, prompt engineering, I wouldn't cover this. So we'll just quickly have one sentence about it. So now you know how to use LLMs, right? So now prompt engineering is nothing but playing around with these messages. Okay, nothing more to it. Okay, so you can try zero-shot prompting, few-shot learning, chain of thought prompting, and there are many concepts around in prompt engineering. So the essence is you need to think, how will I explain a task to a 5-year-old kid, right? Think from that manner and then approach prompt engineering, and then you can come up with prompts easily. So I recommend this short course, which is just 1 hour, and that gives a lot of useful information. Now, one thing you need to note is there are notebooks available in this course, but they are from an older version of OpenAI. If you use the latest OpenAI functions, then you need to make minor tweaks. Okay. Now, I will pass on to Naushad. He will walk us through RAG.
Okay, thank you, Punya. So let me take the screen share. Let me know once you're able to see my screen.
I can see it.
Yep. So retrieval augmented generation. Punya already gave you a little teaser or sneak peek of what exactly it means. Now let me give you. He already gave all the examples. So let me give you a different example. So the name sounds fancy, but the idea is simple and it's been there for quite few times. So consider you worked in a medical and healthcare industry for quite some time, and suddenly you shifted to, let's say, manufacturing industry. Now your manager asks you to, find out something. You have two options: either you learn everything about manufacturing industry and answer the question whatever your manager asked, or request manager to specify some documents where you can find these answers, where you can derive the answer from those documents. The first option is very hard and time consuming. You have to learn everything, etc., etc. Even if you respond, you will not be 100% sure that you will be right at all times. Whereas in the second option, it is much faster. You just need to refer a couple of documents and you will get your answer, and you know exactly where you found the answer or derived the answer from. So the second option, giving where certain piece of information and derive the answer from it, this is called RAG, to put in simple way. Similar to what we used to have in our high school examinations, where we give certain kind of passage and ask some questions. We need to find answers in that passage. Its idea is pretty similar to this. Now let's go to this table. Though, why can an LLM perform text summarization? Because it might have learned the ability to, summarize it based on this pre-training. Why can LLM perform the question answering? Because the data might be available on already in its pre-training data. Why does sometimes LLM provide some wrong information or even make stuff up? Like, we simply call it as hallucination. If you compare it to humans, LLMs, during an examination, if we don't know the answer then to a question, we just write something in the expectation that it may be related to the some original answer. So LLMs are also based on their past knowledge. They will try to make some stuff up. It may not be correct. So the problem at hand we have is LLMs are not trained to generate human-like text. Not true text specific. This based on the next word which has to be generated, as Punya explained. Now idea is we need to ground them to a reality, and so that they don't make up some stuff. In fact, we know everything to solve this, like I gave just an example. So include the relevant knowledge in the context, so the LLM can refer that context and give you the more reliable information. This context queuing is nothing but our prompt. So this is, a pictorial representation of what we have just discussed. So let's assume this is the data that has been trained up to 2021. We also have generic data, and when we give a query to the LLM based on this information it has, assume that this unable to see all the necessary context around it. It is unable to see everything. It it gives us some response because it does not know, it has only outdated information. It does not know the domain knowledge. All like, it cannot explain everything because it doesn't based it do not have any information of where it actually came from. So on the other hand, if we give something like this, like RAG architecture, where we also using some kind of mechanism, we give the necessary context to the LLM, saying that you refer to this context and come up with the answer. Then it will refer to this context and give us more accurate responses. And we know which context we have provided. It is more, reliable and traceable as well. So this is more real life example of
Naushad,
how Bing Chat.
Naushad, can you go back to the previous slide, please? I want to add one point.
Yep, sure.
Yeah, so you can see here, these are the context clue cards here. So these are put based on your data that you collected from interview preparation, right? So these questions are related to sales manager. So now what you can see here is not only do you have multiple clue cards, you also know you have different questions in each clue card. So you have the question and answer. But what's even more important is you have these tags like sales manager, core, handling client, question ID, right? This is the metadata. Now, in addition to the text that the LLM can use, the metadata is also available. So we know exactly from which question this particular, let's say, question and which particular row this question and answer came from the source data. So here we are basically giving it a magnifying glass, right? So that's what is happening here. Yeah, please go ahead, Naushad. Thank you.
Yep, thank you. So one more real life example is how we can, the Bing chatbot. So basically, if you ask a question like who is Colombia's current president, Bing performs a web search and it gets the top search results. It will add those information to the prompt. Like if you look at this, this is the question, who is Colombia's current president? Web search found the relevant context, and this is the information it provides as a context, and we will stitch it to the prompt, and this is the response it can come up with. So how do we leverage our own internal data? So it's, and we don't have any massive search engines like Google or Bing, etc., to work on our internal data because these are optimized to give results in a much better and faster way, but we don't have anything like that for our internal data. So one way we can do this is using semantic search. So those who do not know semantic search, let me give a brief introduction about it. So let's assume that you have some data, mostly unstructured. It can be structured as well. We have some kind of text, basically. So and you have to represent this in some kind of higher dimensional, some kind of numbers or vectors in this case, where everything in this is represented as numbers. This is just a word representation, sorry, vector representation of single words, but in our case it will be on the paragraph level or the entire chunk level. So how do we do this? There is some, we have to do a mechanism of chunking and embeddings to make this, to convert the text into this vectors basically. So what are the tools available for this is, LangChain and Llama Index are most popular ones, but if you have enough Python knowledge, you can do this by yourselves. Chunking and embedding. Chunking is nothing but you have to split the entire text into a smaller number of pieces, and embedding is nothing but I'll explain the next slides. And where you can store this semantic representation is nothing but there is something called vector DBs. Uh, in for structured data, we store this in like tables like MySQL or RDBMS. Similarly, for storing vectors, we have vector DBs. So if we go into chunking, right? So if you go, we have a paragraph, big document like this. We will split it into chunks in this way, like until this point is chunk one, until here is chunk two, and this is chunk three. So in the interest of time, I will not go deep into the code, but you will get the idea. So here nothing but we are just loading the file. we have defined a file name called chandrayaan3.pdf. We are loading the file, and we are saying chunk size is only 500 characters. Chunk overlap is nothing but this chunk or the last few words, 100 words, can overlap with the second chunk as well. These are the separators. Basically, whenever you see a slash in character, then these are we considered as separators. And this is the splitter, and these are the number of additional information you can get from this. This is the metadata and page contents, etc.
Yeah, this here you can use LangChain to do the splitting, or
Yes.
you can also use llama index.
Embeddings. So as we all know, computers do not understand words, so they can only understand numbers. I mean, one or zeros to be specific. Embeddings are nothing but number representation of a text. If we try to condense information from lower dimensions, then we will start losing information. For example, if you plot a sphere, which is a 3D image, to a 2D plane, then it becomes a circle. That means we are losing some information. Conversely, if we try to uh, you know something which is in a lower dimension to higher dimensions, like there will be so much noise. Those who have already worked with images can know that dealing with higher quality images can we smoothen the images to reduce a lot of noise. Here also we have like vectors are high dimensional, so we have to strike a balance between how many dimensions do we want to represent our data. Birth in this case is giving 768 dimensions. So the idea is text with similar meaning or similar representation are very near to each other in the vector search space. So this enables us to give the semantic or similarity search. So if let's take it, let's see the flow. If you have a text, you tokenize it. I mean, tokenization already Pony has explained. So these will be the tokens will be sent to the embedding model. Embedding model will give you the output as the embedding vector. So let's take one example. Let's see let as a single word. If you tokenize it to using birth, which is 768 dimension, then you will have a single list or an array with 768 numbers in it, float numbers in it. If it is sentence embedding, instead of a particular word, you'll convert into embedding vector. You will have a vector of 768 dimension of the entire word. Similarly, for chunks, it's basically you have a chunk of this multiple lines. This everything is condensed and represented as a single vector.
Yeah, what's important to notice is, can you go to the previous one?
Yeah,
Yeah.
sure.
So you see the difference. There is one word that is represented by 768 dimensions, just a single word. Whereas in the second one sentence becomes this, you can see you have much longer sentence. There is multiple sentences in a chunk. Still, it is also represented by a single vector with 768 dimensions. So you can see that a chunk, if it grows big, right, the dimensions remain the same. It is just a single vector. So the information that vector represents will be less and less if the chunk size becomes larger and larger. So that's a challenge that we will come across in many of the applications when we want to do embeddings. Yeah, please go ahead, Naushad.
Yep. So every time we have to convert this text into embeddings, right? I mean, on the fly in the real time we cannot do it. It's more expensive and it's not scalable. So we have to store all this embedding in a particular place. Here we have something called vector DBs. So you have all the unstructured data, like can be images, document, audio, anything. So you could transform this into embeddings. You have all this vector representation. You store it into a vector database. Similarly, you have your query asking for something in a natural language in some kind of text that is also converted into vector representation, and you perform a nearest neighbor search, and wherever it is nearly matching to your nearest query, the data, it will give you as a result. So how to perform this nearest neighbors is there are multiple ways. One of them being the simplest one being the cosine similarity or Euclidean distance, for example. So if you go into, Chroma DB is one of the vector database available, which is easy to install. So here is the code representation of it. First thing is storage of embeddings. Use the given embeddings of a particular text or audio or anything to store. to higher dimensional vector to the actual text. So if you look at this, let's say this is our directory where we are storing the embeddings, and we have to give a collection name. Those who have worked with NoSQL databases might understand what collection names are. It's basically a database name. You can keep it in, you can think of in that way. So we have to give a we have to give some kind of embedding function to convert the text into embedding representation. Here we are using this all mini LM L6v2 model to convert the text into embeddings. This is nothing but just to mentioning that store all the necessary data in this path. So next we are doing get or create collection name, and embedding function for chunk in chunks in the loop. You take all the necessary chunks which I showed you earlier, and give the necessary IDs, metadata, and documents. And you can query saying that when did Chandrayaan 3 land on moon, and if you can query it based on the query text, and you can get the here you can specify how many number of relevant documents or nearly matching documents you can get. Here we are taking the one result, top result. So here Chroma actually, and depending upon the database, it can give you multiple features. For Chrome, for example, Chroma here gives you, filtering and filtering on the metadata or IDs or documents, and also will supports here create, read, update data operations on the data. So now you know all the components need to build RAG. So if you put together everything, you will see something like this. So you have a groundwork basically where you have the domain specific or internal docs. You do the necessary pre-processing and chunking, and you use the embedding model to and store all the necessary data in the vector database. Here you have a retrieval function where your query is also using the embedding model. You get the necessary, you do a semantic search, and you do the necessary filtering, etc. You get the top k matches, and you augment the prompt in such a way that you say that using this context, answer the query, and you pass it to an LLM, and LLM will give you a response. This is another way of representing the same thing. So you have all your documents, convert into chunks. After that, you convert the chunks into embeddings, store it in a vector database. You have a query. Query is also again converted into embeddings, and you search the necessary similarity documents from the vector DB. It will give you some document chunks or the relevant document chunks, and you pass it to the LLM along with the augmented prompt, and LLM will give you the response. So this is the sample code. We're almost out of time, so let me go through this quickly. So this is the without RAG. I think this is already covered by Punya. So basically you have a completion method. You give the model prompt, and this is the output. Here you can see when did Chandrayaan 3 land on the moon, because OpenAI it does not have the necessary knowledge. It will say the mission is currently in development and expected to launch in 2022 or early 2023. But similarly, whereas if you're using RAG, you pass the necessary context in this instruction saying that this is the truthful AI assistant. You give the necessary context using the query, using the data you got from the vector database, and you ask the same response again. Then you can say that the LLM will give you much more better response saying that it's landed on the Wednesday, August 2023. So this is the final context that is prepared by the that is augmented and is passed to the LLM. So you can see it has given all the necessary context. At the end there is a question and it came up with relevant answer. I think we slightly overrun, but I think we have we can take a couple of questions, I guess.
Yeah,
Yes,
thank you,
Naushad.
Naushad.
Yes, thank you, Naushad. Thank you, Punaya. Yes, we can have a few questions.
Any questions,
Anyone? Yes, Vishnu.
I was just clapping.
Vishnu, go ahead.
I was just clapping. Yeah.
Okay. Okay, no problem. Sorry. So we think, yeah. Yes, Arthur.
Actually, Punaya, I had a question.
Okay, go ahead. Is this?
Actually, I want to know what is API endpoint URL.
Pardon me, can you please
Because
repeat? What is?
API endpoint URL. Actually, while trying to generate the data set using LLM, I mean, it not just asked me for the API key, but also asked for API endpoint URL. I didn't know what to pass in that. So
Okay.
yeah.
There is no such thing as URL. So I will share the notebook so you can run it. Only thing is you need to create a .env. It's a text file. You need to put
Okay.
OpenAI API key in that exact
Okay.
format. Okay. So
All
then
right. All right.
it should work.
Okay,
Sure.
so
Thank
yes, Lincoln, Russell, Lincoln, go ahead.
Yeah, I have three questions. My first question will be how LLM knows when to stop generating something, and uh, so should I ask like second question or?
Yeah, please go ahead.
Okay, and my second question will be, for example, if we give a instruction to the LLM, which was not present during the training data set of the pre-training of instructions, then what will happen? And my third question will be, can we get higher dimension for the embedding of tokens more than 768, like for BART or something?
Yes. So, okay. Okay, the last question. Yes, you can have different dimensions depending on your choice of model. So that is fine. All right.
Okay.
For the second one, I'm not very sure. I mean, if something is not part of the instruction fine-tuning, I mean, the performance may not be as per your expectation. So there may be hallucinations. Okay.
Okay. Okay.
All right. And okay.
And my first question was when LLM knows when to generate.
Yeah. So, okay. So what happens is, okay, number one, we would specify what is the maximum number of tokens we need. Okay, that is the limit that we give.
Mhm.
But then the LLMs also naturally understand, or I shouldn't say understand, the generation automatically comes to a logical conclusion because there is nothing further to add, right, to the given prompt. Okay. That is one,
Okay.
and also the maximum tokens that you specify. Those are the two things that I know of. Maybe Naushad can better explain than me. Naushad?
Yeah, I mean, there are some stopping characters. Either you can specify them by yourself. Of course, you cannot do them in the OpenAI or proprietary APIs, but you can do that for the, open source models. You can have your own stopping characters, or based on your pre-training, where it will see, where, I mean, in the model itself, it will see there it should be some kind of stopping character. I mean, there is a start character as well as there is an end character. When the end character is at 8, I mean, given as the response, when it checks for the what is the my previous character to previous characters to generate next token. If it sees the end character, uh, then it will stop the response. Hope this answers.
Like for example, in maybe in ChatGPT, how it knows that when I need to stop generating the answers, like more sentences or something.
Yeah, like I said, I mean, the fine tuning in OpenAI, the GPT team has, I mean, OpenAI team has already fine tuned in such a way that it knows when to give a exact stop character based on this fine tuning or
Okay.
pre-trained data.
Okay. Yeah.
And
Thanks.
how it attains that end character is based on the attention mechanism. It can be flash attention or any other attention mechanism which they have opted.
Okay. Okay. Yeah. Thanks.
Yes, Arthur, go ahead.
Hello. But first, I wanted to ask basically a question on top of the Russell's question. Do I understand it correctly that the dimensions are preset to a specific model? So, for example, if the BARD has 768, or what was it? then it would always have to be 768. So it would always stay the same for particular model.
Okay. Akhtar, I think you're talking about embeddings, not the LLMs, right?
Sorry, can you say that again?
You're talking about the embedding model and not the LLM, right?
Yeah, well, it's regarding the question that Russell asked about if the
Okay, about
dimensions can be very.
about BERT.
Yeah.
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 So the output will always be 768. So this is about the embedding model. If you give, let's say, one word, and the output will always be 768 dimension vector. Okay.
Yeah.
For a second. So if you use a different model, it might have a different dimension, but for every input, it will always give you that same dimension as output.
Yeah. Okay. So I also have two questions. The first one would be, I saw that in the Hugging Face, there are models that called like something GPT. So yeah, are those models like based on the GPT models from OpenAI? They're just made so that they would be open source, or what would be?
Yeah, they are based on, that is, GPT is basically a class of models. It doesn't refer to OpenAI's ChatGPT. Okay, so what people do is they use that architecture and they build on top of that. So they call it as GPT. Okay.
Okay.
Yeah.
And the other question was, when I was doing this course that you provided, recommended at the very beginning of this task, not task, sorry, project.
Yeah, the prompt engineering course, you mean, right?
Not the prompt engineering, but I mean at the very beginning, like few weeks back.
Right. I think at the very beginning. Okay.
Yeah. Then there was a mention of like forgetting, like if you're doing the training, the model can start forgetting stuff. In which part where you had your slideshows explaining the steps, and which step would that be included?
Okay, I did not tell you about that in the presentation, but yeah, you're right. That's an important point. So in the slide where I was talking about the restaurant as well as the LLM examples, you can look at the step of fine tuning. Okay, just before retrieval augmented generation. There you can see that for single task, I mentioned that you can use 1,000 samples. Whereas if you're doing for multitask, then you need to use 100,000 samples. So when you fine tune it on a single task, what happens is you will have catastrophic forgetting, because when you update the model parameters based on just a single task, the model's performance on other tasks may take a hit. So that's what happens. So in order to overcome that, usually people tend to do multitask fine tuning, okay, instead of a single task fine tuning. So that way, they cover the multiple tasks for which they would use the model for, and they would make sure that it doesn't get affected. The other option is using PEFT, parameter efficient fine tuning, okay, where you don't update the model weights, you only add in new parameters. So what happens is at runtime, you load the base, that is the human aligned LLM, and then during training, you would have obtained new parameters, completely new set of parameters called as adapters. So it's basically like putting on a new cover for the LLM. So that cover basically contains the new parameters, additional parameters. And those parameters influence the LLM to give the desired result for the single task. So what happens is for different tasks, you would create different adapters, and at inference time, you can change adapters. Okay. So those are the two different ways in which those can be tackled. So if you're doing a full fine tuning, you do a multitask fine tuning. If you want to do a single task fine tuning, you use PEFT and get the PEFT adapter. right? Which is a very lightweight parameter set. And you would use that adapter set on top of the LLM only for that task, not for any other task. So these
Okay.
are the two ways to overcome that catastrophic forgetting.
Okay. Thank you.
Yeah, we can take few questions and then close the meeting. George, go ahead.
I have small doubt on parameters. What do we call as parameters of the model? Is that a data which we are?
Can you please repeat again? I couldn't hear your question properly.
What do we call as parameters in the model? Is that the data which we are giving for the training to the model, or how we define parameters in the model?
Okay, you're talking about the parameters of the model, right?
Yes, yes.
Okay, the parameters of the model are nothing but the weights for the neural network. So if you remember, in the neural network, you would have inputs, and then it would do right, a dot product. It would add the bias, and then it would apply the activation, and it would give the output. This is a single neuron. So there will be weights and biases for every neuron. So those are the parameters. Those are updated, that is initially randomly assigned, right? And then during training, those weights will get updated, let's say by gradient descent method, right? So during training, they would get updated, and finally, once training has converged, you would have the final set of parameters. And those parameters are the most important ones because that's what is going to guide how the input is going to be converted to the output.
Okay. So
Okay.
the parameters are just calculation of the vectors, right?
Those are the weights that are used in the neural networks. That's what I can say.
Yeah. Okay.
Yeah.
I can understand. I can understand. Thank you.
Okay. Okay. Thank you. Yes, Asya. Sorry. Asya, you can go ahead.
Okay. I just have a general question to summarize. First of all, thank you so much for sharing and giving us support to understanding all of this. My question is, what is the expectation right after this meeting till the next meeting? And what should be the starting point? As Punya has shared that practice so and so code. So what is the best thing? How we start and then go on the next steps and then share on the task for team. So what is the expectation after this call?
Yeah, the expectation is that, okay, those who are not familiar with LLMs, I'm sure this would have given you a good introduction. And I will also share the presentation as well as the notebook. You could practice on them, right? Get familiar with them. And then you can contribute towards task 4. So those of you who are completely new to this, you can keep practicing and you could attend the task 4 meetings, join in the discussions and ask questions. So people will be discussing about approaches. So you can ask questions as to
Yes.
like, why are you doing this? Why are you not doing that? Right. So you can ask them to explain a little bit more so that you can also get that intuition. Right. So
Yes,
people.
Basant, yeah, we have few questions, right? Is that done? Yeah, Basant.
Yeah, I have two questions.
Okay.
They may be very elementary, but I am curious to know what are the
Okay.
factors? What are the factors when we look into when we select a vector DB? Means what factors? Because there are so many vector DBs are there. How do we select or choose a right vector DB based upon the factors? And similarly, when we are creating an embedding for any this RAG application, there are several again. There are not one approach like you can choose a ChatGPT or a Palm, or there are several in the Hugging Face which are open source. How do we again? What are the factors we look into when selecting a embeddings? Yeah.
Okay. So I think the easiest one to answer is how to choose an LLM because I can give you a few points on that. So the first one is the business case that you're looking at, right? So or the use case that you're looking at. So if it is again choosing the LLMs, right? You're specifically asking about RAG. So you need to see what kind of task you are working on. And depending on the use case, you need to see what kind of capability you need and which parameter, that is what kind of size you're looking at, because the performance of models differ based on the parameters size. So a llama 7 billion may not perform as good as a llama 70 billion, right? So that is one factor you need to look at. So what is the optimal range of parameters that you can use, right, to get a good output from that? So that is something you need to experiment and find out. There is no simple way to understand. You need to try out different models and see which ones actually perform zero shot and how good they compare. So that is one way. So that is one factor. The other factor is most important thing is your cost and what kind of infrastructure you can afford and things like that. So that will basically tell you which models you can definitely focus on, because you can eliminate a lot of things which are really expensive, right? So that way you can narrow down based on cost. That is the other thing. Okay. And the third thing is, like, how do you want to use it? That is in terms of whether you want to use it within your company because you don't want to give out the internal data to external vendors, right? Confidentiality, that's an important thing. So if, let's say, you are having a very confidential information, and in that case, you usually go for hosted LLMs within your premises, right? So those factors also affect what LLMs you want to choose. With regard to vector DB, I don't have much experience to tell you like what are the factors you need to consider because I've been only playing around with some of the free options that are available. So maybe Naushad, if you have anything on those, maybe you can.
Yeah, so the
add on to that.
easiest way is, I mean, first before actually choosing a vector DB, you must choose the embeddings. So I think Punya also already explained how to choose embeddings. See whether the training data of embedding model has some similar data or similar domain data of what you are actually working on. Let's say if you're working on banking type of data or some financial, see financial data is already included in the training data set, then you can see uh, some kind of relevance between the financial institution terms related to in that embeddings. Otherwise, the terms like river bank and the actual bank, actually they have very different meanings. But if you don't choose a right embedding model, then they can actually be very relevant. So that's one way you can choose the embedding model. And the next step is choosing a vector DB. I mean, there is no right answer for it. It depends on, I mean, usually how I go for it is there any database which I can easily integrate with my existing infrastructure? That is the first option I choose, because setting up a new environment, especially for a one single vector DB, is particularly costly. So first thing, that's the one way I will check, and next thing is the algorithms they use, the internally whatever they use for the similarity search, whether it is fast enough and compute not very compute expensive, but yeah, does a decent job in the similarity search with high enough throughput and with low latency and high throughput. These are the some of consideration which I take into consideration, but there may be others as well. Hope this answers.
Yeah, thank you.
Yes, that's it from today's. Yeah, anything else, Punya, to add?
I think there is one more question. There is one more hand that's raised, right? I think.
Yeah.
Yeah, hello.
We can only take one last question and then close the meeting.
Yeah.
Yes, go ahead.
Yeah, I think GPT has 176 billion parameters. So does this if the parameters are weights and biases, does that mean these are the weights and biases for the uh, embedding of the tokens?
Okay, all right. So now the embeddings are different. Okay, the parameters of large language model are different. Okay, so they are completely two different entities. Now we are using embeddings okay, because we want to convert from the perspective of retrieval augmented generation, we want to convert our text data into a vector representation, which can help in similarity search. So that's where the embeddings are actually used, and we use a specific embedding model for that. And that model is different from the large language model. Now, as far as the parameters of the large language models are concerned, they are not related to the embeddings. Now, the large language model as such, yeah, it will internally come up with, let's say, it will have internal components which will generate embeddings internally, okay? But that is within the LLM itself, all right? Let's say if you're using a model that has both encoder and decoder, so the encoder output is basically like an embedding of the input data. But that is only within the LLM, it's not given out. So that is processed by the decoder, and then it gives out the output generation, which is words. Now, the embedding models are completely different. They are not directly related to the LLMs. They are only aiding us in terms of creating the vector database. But we need to make sure we use a right embedding model, like Naushad mentioned.
But you said that encoder also has embedding for the LLM, right?
The encoder generates embedding. So it's a form of, if you're talking about an embedding model, it is usually, let's say it's a bird, right? It's an encoder model, right? It's a bidirectional model, but an encoder is the one that generates the embeddings. Okay, so we are using a very specialized embedding model for that. LLM internally generates the embeddings and then it processes them. Okay, but they're not given out as part of the LLM as such.
Okay, so these parameters are for that internal embeddings, or
no, embeddings is an output. Okay, parameters are basically the definition of the model's weights and biases, right? So they are not outputs or they are not inputs. They are the settings for the model. You can see the parameters as the settings for the model's neurons, whereas embeddings are outputs generated by a model.
Okay. Yeah, okay, then thanks.
Yes, thank you all for joining today's GenAI session. Hopefully, Puneya and Noshad covers the 101 and 102 session on the GenAI LLMs and LLM APIs. And thank you all for joining. Have a great day. Bye.
Thank you.
Thank you so much.